Hello, everybody. Hope we're doing all right. Let's go ahead and get on with a lecture. We're going to be talking more about probability here, but this time we're going to be talking about some what we'll call addition rules. And basically, what we're going to be talking about is not necessarily the probability of one thing happening. We're going to be talking about the probability of two things happening and using an or in there. So go ahead and write that using that word or. So maybe like one event or another event happening. And I just want to know what's the probability of that. So let's go ahead and get into this. We'll start off with a definition that's going to be critical to these problems that we'll see. And that's going to be this idea of mutually exclusive events. So two events, we'll call each event mutually exclusive if they can't both happen at the same time. A very classic example of this would be trying to roll, let's say we're rolling a die. If we tried to roll a 2 and a 5 at the same exact time, clearly that can't happen because with one roll of the die, you're either going to roll a 2 or a 5 or a 1 or a 3 or a 4 or a 6. You're going to roll just one number. So it's not even possible to roll multiple numbers when you're rolling one single die. And so if we're talking about two events being mutually exclusive, that's saying that they can't both occur at the same time. Now, what I do want to make clear is that this is a lot different than one event affecting another. We're going to see this in the next lecture, more on this idea of one event affecting another. But here, this is just saying that they both can't happen at the same time. And then we'll obviously contrast this with events are not mutually exclusive if they can both happen at the same time. So maybe an example there is if I say, what if one event is me rolling a 2 and one event is me rolling an even number? Well, clearly those can both happen at the same time. If I roll a 2, that is both a 2 and it's even. So those events would be not mutually exclusive. So let's go ahead and look at an example here to really see what we're talking about. So I want to say, what is the probability that you roll a 2 or a 5 on a die? And that or is really the key word there. That's important because really in this scenario, if I roll a 2 or if I roll a 5, that satisfies this condition of rolling a 2 or a 5. And so the probability should be higher than just rolling a 2 or just rolling a 5. And so the very first thing that we want to think about, we want to ask ourselves the question, are these events? And when I say events, what I mean is roll a 2 and roll a 5. Those are my two events. Are these events mutually exclusive or not? And when I look at this, as we described before, it seems to me as though they are. And we think that they are because it's not possible to roll a single die and roll both a 2 and a 5 at the same time. At best, it's going to be one or the other, but you definitely can't roll both at the same time. So these events cannot happen at the same time. So they're going to be mutually exclusive. So let's go ahead and move on. Let's talk here about how we might want to go about approaching doing this problem. So if we have the event that we're trying to roll a 2 or a 5, well, I roll a 2 1/6 of the time. Because if it's a six-sided die, then there's 1 out of 6 chances that I can roll a 2. And then likewise, it's the same thing with rolling a 5, 1 out of 6. So it seems to me like the total number of ways to roll a 2 or roll a 5 is going to be 2 out of these 6 ways. And you'll notice all I'm doing is I'm just adding these together. And I'm saying, hey, there's one way to roll a 2, there's one way to roll a 5. So there are 2 total ways to roll either a 2 or a 5. And that gives me a probability of 1/3 right there. And right here, we've actually found it. This is the probability that we roll a 2 or a 5. And it's fairly simple because these events are mutually exclusive. So what I want to do is I want to continue on. I actually want to do another example here, and it's going to look similar, but it's going to be slightly different. So let's say that we're drawing from a standard deck of cards, or a 52 card deck, and I want to know what's the probability that I draw a 7 or I draw a spade. And we could start with this, and we could say, all right, let's go ahead and look. I could draw a 7, and I can draw a spade. And the probabilities of each of these, the chance that each of these happens, well, there's 4 sevens out of the 52, and there's 13 spades out of the 52. So it's natural to think, all right, let's do exactly what we just did, and let's add these together. Because, hey, I can roll a 7 or I can roll a spade. And so if either of them happens, then we're sort of good. And we say, hey, there's 17 ways out of 52 for this to happen. But the problem with this is that there's actually some overlap here. So this is bad. Because it is quite possible to draw a 7 of spades, right? Clearly there is a 7 of spades. So there's actually a card here. There's one card out of all 52 that satisfies both of these probabilities, or excuse me, both of these events of drawing a 7 and drawing a spade. So let's say that we did this. Let's say, obviously, as I just said, there's an issue that the 7 of spades, it's both a 7 and it's a spade. So if we just count the number of 7s and we count the number of spades and add them up, it doesn't work because we're double counting the 7 of spades. If we do that, if we just do this 17 over 52, if we just add the 4 and the 13 ways that we can draw a 7 of spade, we're double counting one of those ways. And we could draw a little picture here to remind ourselves of what this might look like. We could go back to sets here, and we could say, all right, draw a 7 is over here, and draw a spade is this circle over here. And if we were to count up these number of ways, we would say, all right, drawing a 7, well, there's 1, 2, 3, 4 ways. I'll just put some dots there. And for a spade, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a 13th way. But as we've said, one of these dots that's on here is actually both a 7 and a spade. So what I want to make sure I do here is I want to make sure that I actually include right in the middle that one dot. This is what we've talked about before with sets about an intersection. And we've seen before that if we want to find the number of elements in a union, then we can actually count up how many are over here, or excuse me, we can count how many are here. We can also count how many are here, but then we can subtract off these extra that we've double counted in the middle. And we saw this in the format of this formula here. We saw n of A union B is equal to n of A plus n of B minus n of A intersect B, right there. And so with that, we have a very similar formula here. And in this case, we can sort of do this problem slightly differently. And we could say, all right, so if I'm double counting that 7 of spades, let's come right back here. What I can do is I could say, all right, well, there's the 17 ways that I could count a 7 or a spade, but I'm double counting one of them. So why don't we just subtract that off? And so I'll go ahead and do this just in blue down here. We'll have that 17 over 52. We'll subtract off the way that we've double counted. We're going to have 16 over 52. We could simplify that. We could divide by 2. We'll get 8 over 26. We could divide by 2 again. We'll get 4 over 13. And there we go. That would be our answer right there. And so what we're seeing here is that this is actually a perfect example. I haven't stated this yet, but this is a perfect example of when these events are not mutually exclusive. So the events of drawing a 7 and drawing a spade are not mutually exclusive because they clearly can both happen at the same time. You can draw the 7 of spades. So they're not mutually exclusive. So this leads us, and we'll keep an eye on this formula. This leads us to sort of the big slide for the lecture. And it's going to be two formulas. And the first formula says that if two events are mutually exclusive, then to find the probability that either of them occurs, we just add the individual probabilities. And we did that back there on that example of rolling a 2 or a 5 on a die. We just took the probability of rolling a 2, we took the probability of rolling a 5, we added them together, and that gave us the probability of rolling either. But if these events are not mutually exclusive, then we have to do exactly that, but then we have to subtract off this sort of double counted part. We have to say, hey, these are the number of ways that I can draw a 7. This is the number of ways I can draw a spade. But hold on, one of those ways is that I can actually draw both at the same time. So I want to make sure I subtract that off. And hopefully you notice how similar this formula right here looks to this formula right there. It's basically the same exact thing. So we're seeing sort of a connection between sets here and some probability. Cool. So one other thing I want to mention here is that this formula up above, you could very well include, basically you could have the same formula. You could include this P of A and B in this formula. The reason we don't bother is that in the event that A and B are mutually exclusive, so if A and B are mutually exclusive, this is equal to 0. So we just don't bother putting it there. But basically, this is our standard formula for any sort of or probability. And then you just have to figure out what P of A and B is. And sometimes it's 0 in the case that A and B are mutually exclusive. And sometimes it's not 0 in the case where A and B are not mutually exclusive. So however you choose to remember these, if you want to remember them separately, or if you just want to focus on this and just keep in mind that, all right, I'm going to always have to consider what P of A and B is, either way is fine. It doesn't really matter to me. So let's go ahead and move on. Let's do another example here. So we're going to draw a single card from a deck, and we want to find the probability that it is a king or a black card. And so what we've got here is, first off, there's 4 kings and there's 26 black cards. So all of those black cards are going to be the spade and the club, and there's 13 of each of those. And then there's obviously 4 kings. So we have sort of a double counting here, though. There are in fact 2 cards in our standard deck that are both a king and are both a black card. And so those cards are the king of spades and the king of clubs. So we know that because there's actually 2 instances here, but because there's instances of drawing a card that is both a king and a black card, then we can actually say that these events are not mutually exclusive right there. Because you could draw the king of spades or the king of clubs, and it would satisfy drawing both a king and a black card. And so these events are not mutually exclusive. We're going to make sure that we deal with this formula. We make sure that we subtract off that probability of both of them happening. And so when we do that, I haven't filled this in yet, but we're going to have the probability that I can draw a king, the probability that I can draw a black, and then we're going to subtract off the probability that I draw a king and a black card. All right, so if I were to fill these in, the probability that I draw a king is going to be 4 out of 52. The probability that I draw a black card is going to be 26 out of 52, as we mentioned earlier. And the probability that I draw both a king and a black card is 2 out of 52, because there's 2 of those, the king of spades and the king of clubs. And so we can work all this out, and you can see those right there. 28 over 52, we simplify by dividing both numerator and denominator by 4, and we get 7 over 13, and that's our nice answer right there, 7 over 13. Great. And so there is another example of this or calculation. And what we want to try and keep in mind is this difference between or and it goes back to sets and logic. So when we say or, I just need one of those things to happen in order for the event to hold. If I say and, I need both to happen. So this problem becomes a lot different if I say, what's the probability that it's a king and a black card? That we've actually figured out already. It's just 2 out of 52. And so what we'll talk about in the next lecture is we'll actually see a little bit harder ways. We'll say, hey, how do we actually calculate this part right here when it's a little bit tougher than just counting things up? Obviously, with a deck of cards here, we could just kind of count, hey, king of spades and king of clubs. But we'll want to make that distinction between using the words or and. They are very important. So we'll go ahead and call that the lecture. That'll be it on addition rules for probability. We've dealt with our addition and even a little bit of subtraction there. So that'll be it for addition rules, and we'll move on next time to multiplication rules.